is going to give us a report on complexity holography and quantum field theory. Thank you very much.
Okay, oh, it is working. Excellent. So thank you all for making it here this morning. At Steve's behest, what I'm going to do is split the hour up, and he wanted to have a discussion or make sure that there was time for a discussion. So I was going to talk for about half an hour, and then I had two special guest speakers, one of whom is Ted and the other one whom is Alex, who didn't make it to the room yet. So hopefully he'll be here, Alex Boleyn. And they'll give some small reports on what they've been thinking about with respect to holographic complexity. And then we'll just open it up to questions and answers. And so there's my title. I also want to credit, I've in the past couple of years been working on these ideas, but I got to work with a lot of smart people, and there's a long list, and that includes Ro, who's sitting right there. And, well, you can read the rest of them. Okay, so anybody, well, I guess like Raphael, I've got an algorithm for my research, and so anybody who's seen me give a talk in the past, I don't know, 8 years knows that I start with this slide here. But this slide is not about complexity. Instead, it's about holographic entanglement entropy. And what we found was that that was a very fruitful forum for a discussion between the boundary and the bulk. And in particular, we learned new things about quantum field theories, and we also learned new things, or we gained new insights into gravity and even quantum gravity. But then a few years ago, Lenny came along with a title saying provocatively, entanglement is not enough. But what he really meant is that entanglement entropy is not enough. I mean, generally the philosophy or the perspective that had emerged is that entanglement was an essential ingredient in the emergence of the bulk space-time in ADS-CFT. But what Lenny was pointing out is that this is really just one probe of the entanglement structure of those states of the theory, and that we should be willing to think about other kinds of probes. In particular, in Lenny's paper, what he was concerned with was that when we use holographic entanglement entropy, it's very difficult, or in all the examples we know, we can't really probe very effectively the region behind the horizon of here an eternal black hole in my Penrose diagram. And so he wanted to find new observables that would be more effective in telling us what's going on deep behind the horizon there. And one of the things one might remember is that entanglement entropy or Rayleigh entropies are things that really probe the density matrix by evaluating or probing various combinations of the eigenvalues of the density matrix, or a reduced density matrix. And what Lenny was looking for, or suggested that we should be looking for, is some more sensitive probe of our favorite density matrix. And in particular, it might be sensitive, for example, in this example here, it might be sensitive to things like the phases, which wouldn't show up in a formula like that. Of course, his suggestion was holographic complexity, which is basically the subject of half of the talk. So I should start by giving a quick introduction to complexity, since not everybody may know what it is. But basically, complexity is what our intuition says that word means. It's how difficult is it to implement something. For example, how difficult is it to organize a conference where we start at the same time every day? I mean, but today the task that I'll be focused on instead is how difficult is it to prepare a particular quantum state. And we're going to use something known as the quantum circuit model, and it goes something like this. First of all, we start with a reference state, and that is supposed to be simple in some particular way. In our discussion, what we want to do is we want to probe the entanglement structure of a family of states over here. The simplicity here is usually described as saying that our degrees of freedom are not entangled at all. And so what we're going to do with our circuit is we're going to start with an unentangled set of degrees of freedom, and with the circuit we're going to build up the entanglement that appears in our final state. So there's a simple reference state, and of course what I'm looking for is a unitary to make a transformation from the reference state to our favorite target state over there. But the rule is going to be that we're going to build this out of an essential set of Lego building blocks or a simple set of gates, which typically only act on a few degrees of freedom here at a time. And so from some quantum information paper, here's a set of universal gates that we might work with if we're talking about qubits here. But the rule is going to be then that I'm going to have a certain set of building blocks, and I'm going to put them together in various ways to try and implement this transformation. There'll be many ways to do that, but it may also be true when I'm, here's an example circuit. If I'm working with discrete elements like that, it may be that I can get very, very close to the state that I'm interested in, but I won't be able to actually hit the target state right on the nose. And so in the typical discussions, you'll find that there's a tolerance. We'll say that I want to get to the target state within a certain epsilon by some measure. The details of this are not important. And in particular, you'll see later in the talk that they're going to, that part of the discussion for our purposes is not going to be relevant at all. What I said was there are going to be lots of ways to put the gates, these universal gates together to implement this transformation, or at least approximately. And what I'm supposed to do is I'm supposed to scan through all possible ways to build that circuit, and I'm supposed to find the circuit that's shortest, or I'm supposed to count up the gates required in each different circuit, and I choose the optimal one, the one using the least number of gates, and the counting of the gates then is what we call the complexity. One of the annoying things that we may notice already at the get-go here is that I made a bunch of choices and I was kind of vague about what those choices should be, and you might worry that those choices are going to affect our answers. In particular, I chose a reference state, I chose a set of gates, I chose a tolerance, and if I make a certain set of choices, if Jonathan there gets off his email and makes a different set of choices, we may get different answers for the complexity here. And so one of the tasks here in understanding complexity and its application to holography is to understand, what is the useful physical information that we can extract from this? What are the robust questions that we can ask, where we can get something useful out of it without worrying too much about these choices. Okay, so Lenny not only introduced the concept of complexity, he introduced, with various collaborators, different proposals for what kinds of gravitational observables we should be thinking about. And these typically go by the two names complexity equals volume or complexity equals action. In the first case, so here I've returned back to my Penrose diagram of the eternal black hole. Here what I do is I choose my favorite time slices in the boundary theory, and I imagine that there's a boundary state defined on those time slices, but in the bulk what I do is I think about all codimension 1 geometries that stretch through the bulk, reaching between those two boundary slices. And then what I do is I extremize. I find the maximal volume slice, and in that particular case, I equate that to the complexity. And to make it dimensionless, I have to introduce Newton's constant here, and in fact, I have to introduce an extra scale. But I'm not going to comment more on that because I know Ted has some ideas about that. So that's one choice. The other choice, or the other suggestion, is complexity equals action. In that case, what I'm really looking at with this diamond here, or the pink region, is the domain of dependence of this particular Cauchy surface, or any one of the Cauchy surfaces that may have gone into that extremization procedure. And what I'm supposed to do here is identify that region of the space-time, which is called the Wheeler-DeWitt patch, and then I evaluate the gravitational action on that region of the space-time. And again, there are small factors, but essentially what I'm doing is I'm equating the action with the complexity in this situation.
What do you do with the singularity?
That was something I was supposed to say. I welcome questions, but one of the things I'm going to do is I'm going to table some of those questions for the discussion section. So there's a good question, what about the singularity? Yeah, so I should have said that I encourage any questions you want to ask, but as in your case, I may table some of them because it's... by design, both of these constructions give us something that's going to be, or it turns out that it probes the region here behind the horizon for arbitrarily late times, t left and t right. And since Fook is in the audience, I'll say that, there have been a number of other proposals or variations on this. And so there's what has, I think, become known as complexity equals volume version 2.0, where they realize that you can just take this region of space-time, so the Wheeler-DeWitt patch, I can evaluate the space-time volume there. And in fact, and then they have a similar equation. They're going to equate that space-time volume with the complexity, but it satisfies basically all the same properties that you might, the favorable properties that these two observables satisfy. Yeah, Steve.
Rob, you may want to also table this, but often I think, okay, when you're looking at these geometries, say the volume, it's the volume of the very long...
This one?
Yeah.
Yeah.
Yeah. You go very far into the future where the slice is extremely large.
Yeah.
And at that point, it's not really clear anymore that the classical geometry is a good description of the quantum state. Mm-hmm. And so what do you say, what's your take on that?
No, yeah, so what I'm doing here is purely geometric. Well, I could picture down there, but there's, yeah, I would only believe that this is true as long as, the classical geometry holds. But that, from Lenny's perspective, that becomes a feature, not a problem, in that, in the complexity, you can expect that you're going to wander out in the space of states. But eventually, there are going to be shortcuts. There are going to be other trajectories. It won't be a continuous family of trajectories as we're evolving in time. And he wants to equate the idea, he wants to equate the idea that when I reach a region, far, far away or deep in the space of states, that when these shortcuts are becoming relevant, the behavior of the complexity changes, but he wants to equate that with a time when I'm not really allowed to use the classical geometry anymore. But if you want, we can discuss more later. I don't know if that... one of the things I did is I introduced the idea of the observables, but I didn't tell you why he thought that these were appropriate to equate with complexity, and in fact, I'm not going to. Yeah, okay, we're on time. But there are a number of different reasons or stories in some cases that we can tell each other that suggest that these observables and their behavior in different situations that they are behaving in a way that I would expect complexity to behave. And if you want me to expand on that, I'm happy to, but right now I'm just going to keep moving on. I'm just going to say that there are excuses, that we should really think that these might be complexity. Yeah?
So probe the phases. Can
Yeah.
you say something about how this would probe the phases? Again? It's fine.
One of the things that's clear is that this is more sensitive to the state. I mean, one of the things that's clear is that this really isn't a property of the state itself. And like the eigenvalues of the density matrix are some kind of invariant characterization, independent of unitaries of a particular reduced density matrix. Here I've really got a reference state, my favorite reference state and the target state. And so it's become more sensitive. I can't say in a mathematical way but beyond that, but that's sort of an intuitive picture that we've got an increase, or we've got certainly a different perspective on the properties of the density matrix. I'm already behind, but I was just going to say, what do? You can do all sorts of studies of these different observables. One of the early ones that we did is you can ask the question, okay, I've got the set of degrees of freedom for 2 copies of the CFT. There are 2 states or 2 obvious states that I could prepare. I could take both sets of degrees of freedom and prepare them into the vacuum state, their individual vacuum states. Or we also know about this entangled state, the thermofield double. And so I could ask for the complexity of that operation or the complexity of that operation and compare them and ask, was there more complexity here or here? And so there's now a gravitational version of that question here I'm using complexity equals action, but essentially you evaluate this action, you subtract 2 copies of the action on the Wheeler-DeWitt patch and empty ADS, and you get some number. And it turns out that the number is proportional essentially to the thermal entropy, or you can think of that as the entanglement entropy in the thermofield double state. You can do a similar calculation where complexity equals volume, and you get a very similar answer. And so this might be saying that, well, this is one of these realizations of having different sets of rules giving you complexities. Well, the details of the answers don't agree. There seems to be some robust physics here in that they're both talking about the entanglement. Aidan.
Yeah, so do you have an idea like what the reference state is in this case in the CFT?
Okay. Reference state.
Okay.
Oh, Jonathan. Everybody's questions get tabled at this point, but go ahead.
Why is it called a complexity formation, and why is it a complexity? It doesn't look like it's a monotonic in anything.
Yeah. No, this wasn't. It was called complexity of formation because that was a fanciful name we gave it. But it's really not an individual complexity, but I've got a set of degrees of freedom, and I'm comparing 2 different kinds of states. The thermofield double, or 2 copies of the vacuum, and then I'm just taking their difference, and I'm asking, is there more complexity involved in this preparation or in this preparation?
You mean more complexity involved in starting from, if I started from this initial state?
No, I'm imagining that it starts with the same reference state in both cases, but I can prepare the vacuum, or 2 copies of the vacuum, or the thermofield double. I mean, it wasn't immediately obvious that this had to be a positive number. It could have been, I can tell stories where it could have been the other way around. But it turns out that it is a positive number, and it's reflecting the entanglement entropy between the 2. Yeah?
Why does everything vanish in 2 dimensions?
I'm not even going to table that. It doesn't really vanish. It's just, this is really an expansion. There's a whole series of terms. And so what's vanishing is the first term that's proportional to the entropy. And there's the next term in the expansion is a constant. It turns out it's proportional to the central charge. And oh, yeah, okay. So you can do lots and lots of exercises like that, but you come back to the question, what do I really mean? What am I really trying to compare this to in the boundary theory? Again, if I think about holographic entanglement entropy, one of the pluses there was that there were situations like two-dimensional conformal field theories where we had a good handle on doing calculations with entanglement entropy, or of entanglement entropies, and we can compare to the holographic results, and we could say this is matching or it's not matching. In this case, we have much less of a handle of the, what does this really mean in a quantum field theory? And so, making those comparisons between, doing calculations in the bulk and saying this is a good answer or a bad answer vis-a-vis complexity is much harder to do. And so another part of the program is asking or trying to get a handle on this answer or that question. And so again, here were the rules about complexity, but we're going to try to apply it to a quantum field theory. And so this is something that I did with Rho. We're taking baby steps, and so we started with the simplest possible quantum field theory we could think of, namely a free scalar field theory. One of the things you learn from the holographic studies, or you might intuit by thinking about complexity, is that it's UV divergent. And so we'd have to introduce a regulator, and so the way we did that in our paper is we thought about having a lattice regulator, but in doing that we really reduced it down to a much less intimidating problem. Now it's really a problem in quantum mechanics. What we're studying is an infinite family of coupled harmonic oscillators, and we're going to ask about complexity in that context. So one of the questions, or one of the ingredients, was a reference state. And so the reference state that we chose is something that goes by the name of factorized Gaussian. So the degree of freedom on each lattice site is in some Gaussian state, but it's independent of all of the other degrees of freedom. And so this is an example of a state where all of the degrees of freedom have been unentangled or disentangled. We need some gates. Well, in quantum mechanics, the natural thing that we work with are the x's and the p's, the positions and the momenta, but it's easy then to build unitaries. You just take some x's and p's, put them up in an exponential, throw in an I, and the other thing that we throw in here is an epsilon. That epsilon is going to be a small parameter, because what we would like is that the gates actually, when they act on a state, that they make a very small change. We don't want to make big changes. Instead, we want each gate to make a small elementary change on the state. And so this is something that's going to characterize our complexities. Well, it's going to disappear in a moment, but it's there to indicate that we're making small changes with these gates. The last ingredient that we need is a target state. And so some target states, with Rho, what we looked at was the ground state. With some other folks, we looked at the thermofield double. One of the important properties of both of these situations is that they're Gaussian states. And in that respect, it simplifies the problem. And at least for this particular case, that was why we could just look at a simple set of gates like this. We didn't need anything more complicated. It's a slightly larger set of gates that you need here to properly study this situation or the time evolution of that situation. But it's a relatively simple constrained set of gates. So what am I supposed to do? I've got my reference state. I've got my favorite target state. I'm supposed to string together these gates. I apply them with some particular power in some particular order. And then I add up these exponents. That's counting the number of gates here. And that's what I call the circuit depth. The reason I'm calling it the circuit depth is that this is just some random string of gates. Well, it's not a random string of gates. It implements the transformation. But it's by no means an optimal string of gates, or I don't know that it is. And so for the general circuits, I call it the circuit depth. If we can find the shortest possible gate, or the circuit, the one that minimizes this number, then I would call that quantity the complexity. But how are we going to do that? Well, what I'm going to do, or what we ended up doing, again at the suggestion of our friend Lenny Susskind, is that we borrowed an approach by Mike Nielsen, who in turn was borrowing ideas from Hamiltonian control theory. So he was interested in a qubit problem up there, but basically one of the points that he made is it's easier to work with smooth functions if you want to optimize something. And so we should have a continuous representation of our circuits rather than working with discrete elements. And so the way that we represent the circuits is something like this. So the O's here, these are the generators that we had for the gates. These are the operators that appeared up in the exponentials. These functions y, there's a component of y for each one of the generators. You can think of those as on-off functions. They tell me when I'm turning on a particular gate and with which strength I'm turning that gate on. You can see that there's an integral over a variable s, which is labeling the position in the circuit. And so it runs from 0 to 1 as I run from left to right. So if I'm, no, right to left. Sorry, I read that backwards. So if I'm at s equals 0, I'm at the first gates that are acting on my reference state. As I progress to higher and higher values of s, I'm further and further down the string of gates. So this is kind of like, or you may have some intuition from Wilson lines, but it's really an operator statement, or it's a construction of a unitary there that's implementing that transformation. He also suggested that, when you're doing this, when you're building up your state with a chain of gates, you're not just defining a single transformation, but you're actually defining a string of transformations or a series of states. And so he said you should, or another useful thing to do is think about the circuit or pieces of the circuit. Think of it as a trajectory through the space of states or through the space of unitaries from the identity at s equals 0 out to whatever our final transformation is that implements the desired transformation. And so here essentially I'm doing the same integral, but I'm only going up to some value s. I'm not going all the way to 1. And in that particular context, this collection of on-off functions you can think of as a tangent vector to the trajectory or a velocity vector. So here are, this again is the problem we're working on. In optimizing the trajectory, what I'm really, or I can start to draw an analogy with a classical mechanics problem where I'm determining the motion of a particle by minimizing some action. What action am I doing? Well, I'm trying to minimize the cost of my circuit. And so in the context that we had before, what I'm doing is I'm adding up these exponents for each one of the gates, or I'm adding up these on-off functions as I go along the string from 0 to 1. And so if you read Mike's paper in more detail, what you'll find is that the extremal path through the space of unitaries is actually a geodesic in something called a Finsler geometry if I'm using this particular cost function. But he also said that you might think about other kinds of cost functions, and so this might be one that's also more familiar to us as physicists. This is like the square root of x dot squared, and so this is a geodesic in a more familiar Riemannian setting. We might make it even more familiar by adding in some extra weights there, which would say certain gates cost more than other gates, or certain directions in our space of unitary cost more than other directions. And so at this point, you do lots and lots of calculations, and you end up with when we're looking at the ground state, you end up with an answer that looks something like this, which unfortunately I'm going to rush through. But essentially, at the end of the day, it turns out that the way you should think about, or the best way to organize the problem is in terms of the normal modes on our lattice. And essentially what the circuit is doing is, in terms of the normal modes, our ground state is still diagonal, or it's still this simple Gaussian. In terms of the ground state, the only difference for the target state is that each one of the normal modes has a specific physical frequency associated with it that's given here. And so what the circuit does is it squeezes a particular normal mode from the Gaussian that it started with to the physical Gaussian specified by the physical frequency. And you end up in a with a particular measure where I've allowed for an exponent here, alpha, a sum of a bunch of logs that look like that. Now, just from our field theory intuition, we know that a sum like this, or one can intuit that a sum like that is dominated by the ultraviolet contributions, at least in higher dimensions, and those turn out to be the frequencies where the momentum vector is of the order of n by 2. Again, as it says there, I'm thinking about an n by n by n lattice of sites. And very crudely then, out in the UV, these frequencies are of the order of the inverse lattice spacing. And so this simplifies. I just stick in 1 over delta here, and I get a quantity that is essentially the number of sites to the logarithm of, well, it would turn into 1 over delta times this frequency omega naught, which appeared in the target state, or the reference state. And so you get some very simple answer. There's a question you might ask is, well, what am I supposed to choose for omega naught? And so there are different choices you might make. You might just leave it there and you say that's part of the complexity model, it's new scale. You might say that it's something that has to do with the size of the system, or you might think it's something to do with the size of the, or the UV cutoff, the lattice spacing. And that changes the details of the answer. None of those might seem particularly compelling that I make any one of these choices. They all have advantages and disadvantages. But one of the interesting things that we found was that we had done a similar set of calculations in holography, and we had looked at the UV divergences, in particular for holographic complexity. And there was also an ambiguity. You were forced to choose a new scale. And then the question is, how are you going to choose that particular scale? Was it going to be a new complexity scale, or was it going to be a physical scale? Again, there were advantages and disadvantages to all those. But you can see there's a match between this side and this side. When we wrote this paper, I thought this was a problem and there might be an issue with holographic complexity. But then with Rho, we did the simplest possible complexity calculation, and we found that exactly an ambiguous scale appears, and that it gives you the same set of pros and cons there. And so,
just say a tiny bit more about what this length is on the right-hand side. I mean, action is dimensionless, so it looks like you don't need to introduce any length.
I certainly can, but I won't right now. So there are other comparisons that you can make. Let me, reference scale. Reference state, reference scale. I'm just running behind already. The only thing I want to say here is that, just like there's a textbook definition for holographic or entanglement entropy, there's a textbook definition for complexity. And that's really what we're using here in our calculations for the quantum field theory. Entanglement entropy really took off when, Wilczek and friends, or Calabrese-Cardy, showed us that, there were path integral manipulations that you could do that gave you something related to, or would lead to a calculation of entanglement entropy. And so, a real question is, well, how do I go beyond this textbook definition and come up with something that's perhaps more familiar on the HEP-TH archive using field theory techniques. There are a number of different suggestions where what they're trying to relate the complexity to is something having to do with path integrals, where we're optimizing the resources for a path integral construction of your favorite state. And so Tadashi and collaborators came up with a particular suggestion. There's a slightly different description of it here last summer. And Bartek Czech has done something similar where he's more motivated by the Mira network construction or tensor network renormalization, but it's a very similar idea. This is more tensor networky. This is more path integrals. But I'll stop there and I'll say there's lots to explore, but I wanted to hand it over to my friends before we get into the question and answer. So I guess I'm going to pick on Ted first. I see Alex made it. But we should turn this off. Or if, Ted, do you want to?
I'm using the board.
Or I assumed you were.
Yeah.
Yeah, okay. So here's a board. Can we turn off the projector?
Yeah.
Oh, that was easy. Oh. Sorry, Ted, do you want to?
Okay. Let's see. So I should take 5 minutes. Somehow. First, I just want to say that so I'm barely involved in this field, but I got pulled into it by Fook, who's a postdoc at Maryland, and that we wrote a paper. I've been involved in one paper on it, and that paper was co-authored by Josiah Couch, Stefan Eccles, I think like that, who are students at UT Austin, Fook, Wen, and myself. So the main message I just want to get across is that it's a great paper, and it's got tons of interesting things in it, and you might want to look at it. Okay, so that's it. I think I'm finished. So Lenny, we have quite a different perspective, I think, from what Rob discussed, in a way almost completely orthogonal, in the sense that he decided to focus on trying to make sense of the UV structure in complexity. And we took the viewpoint that it seems like maybe really we should just face up to the fact that the ambiguities in the notion of complexity are sort of inherent, and the UV, and therefore the UV answers you get are going to be completely dependent on your choice of reference state and gates, and there's no correct choice for those, so you just shouldn't focus on that, and you should really be looking at, well, the more interesting or useful part is the robust part, which comes from what occurs in thermal states or in the IR. And I just want to emphasize, what got me initially interested in thinking about this was hearing Lenny give a talk where he just pointed out the geometrical fact that if you have the thermal field double state and you pick times on either side, as Rob was showing, then there's some maximal volume slice of space-time that goes through the middle, and that as these times go towards the future, the length of this slice grows, in fact, without bound. There's some surface here which we can call the final slice, a completely non-singular surface, which is just the one beyond which you shouldn't go if you're trying to maximize volume, because getting closer to the singularity shrinks the dimensions transverse to this. And so going closer just doesn't help. It's better to stay there and let the surface just stretch more. So as time goes to the future, the maximal volume slice sort of hugs this final slice and becomes arbitrarily large. So this is a diffeomorphism invariant construction, namely the volume of the slice as a function of the time, and it's growing without bound, even though on the boundary you just have a thermal state, which is supposed to be equilibrium and nothing is happening. So that's curious, that in equilibrium nothing happens, but here's something happening in the bulk very dramatically, this unbounded growth. So what is it that's growing? I took Lenny's question to be that, actually, initially, that what motivated him. But I don't know if that's true. But anyway, one talk I heard him give is he put it that way. And then he proposed, well, what's growing is this complexity. But what is the complexity? Well, it's only growing once you're into the thermal phase. And so then the complexity is just sort of like the complexity of any microstate of the thermal ensemble relative to any other one. It doesn't matter what you started with, but what matters is that you're starting at the thermal scale with some random microstate, and then as things evolve, as the microscopic details of the thermal state evolve, to get from one of those microstates to another is complex. And that's what this complexity is measuring. So that's the general viewpoint. That means that when you cut up, in fact, the volume of this slice is infinite. That divergence corresponds to what Rob was just talking about. It's infinite because of the edges have infinite volume, and that's the IR in the bulk, but the UV in the field theory. So the divergence is a UV divergence, and wherever you put this cutoff, let's say a cutoff radius, doesn't matter, in the sense that the growth of the volume that's happening as time goes on is all behind the horizon. And you'll just change the additive constant by changing where this cutoff is. Which leads to the idea that maybe you should really just cut off at the horizon, because that's all that matters anyway, really, in this discussion. So we question, part of our paper is asking, could we make sense of the whole story by just saying, the natural cutoff is the horizon scale. That's the thermal scale. And that's where, somehow this notion of the complexity becomes robust, because the temperature sets a scale relative to which you should do everything. All right, so that's the general philosophy. Now, another thing is that, based on thinking of it that way, Lenny anticipated that the rate of change of the complexity with respect to time should go like the number of degrees of freedom that are getting complex or that are being manipulated. That's like the entropy of the thermal state. And then each one of them has some transformation on the time scale of the thermal time, which is the temperature divided by h bar. So the expectation is that the rate of change of complexity in time should go like this. And what I was expressing before is the idea that really the absolute value of the complexity itself is ambiguous for a good reason and shouldn't be tried to pin down. But this rate of change is the thing to capture. Okay, if you do this and then you look at black holes, what should the complexity be equal to? Lenny inferred that the complexity, or at least up to an additive constant, should go like the volume of the slice. I'm going to put all the constants in right now. H bar times Newton's constant times the ADS scale. But that was only provided you had a large black hole. So the horizon radius R plus is much greater than, well, actually not much greater than, is greater than or of order the ADS scale. But if it's a small black hole, then to get this to agree with this formula, he had to divide by a different length scale, which looked kind of fishy, and that length scale was just the horizon radius. So this is for R plus less than L to ADS. Now, one of the things in our paper, one of the many fascinating things in our paper, is that these two scales are both equal to the time it takes to fall from the horizon, for example here, or actually from anywhere near the horizon, to the final slice. So let me call that time tau f, f for final. then both of these formulas are equal. It's a strange thing. So for a black hole in in space-time without a cosmological constant, the larger the black hole, the larger this time would be. But with a negative cosmological constant, it saturates at the ADS scale, and then no matter how big the black hole is, this is still the ADS time scale. There's actually a very good reason for that, also explained in our paper. I mean, you can get it from the formulas, but we gave a nice reason for it related to the methods of singularity theorems, actually. Okay, so let's see, I think I better say this very quickly. Yeah, I just want to mention one thing really quickly. The idea of cutting off at the horizon, one thing we worried about was, is this compatible with the switchback effect? One of the litmus tests of this idea of complexity equals volume or action was that it satisfied the property that the complexity satisfied the switchback effect, which I can't go into right now, but we checked that it does, provided you include the volume behind the white hole horizon, which actually we argued made sense because the white hole is a black hole backwards in time, and the switchback effect concerns looking at evolution that's partially backwards in time. But the full switchback effect account takes place just within the black and white hole horizons, and there's no need to consider anything outside. So let me just mention quickly, I guess, one other. How do you manipulate this?
No, it's telling you don't have more time. Just use the space on the board.
Okay. One other key thing I would say in our paper, among all the other fascinating results, is the idea of the volume flow or the gate current. So it turns out if you just given a foliation of the boundary here, you get a foliation of the bulk by maximal volume slices. And orthogonal to each slice is a unit time-like vector. And the divergence of that vector field is zero precisely because these are maximal slices. So this unit time-like vector is a conserved current. And its flux is the flux of volume. And you could think of it as the gate current in the bulk. And it's interesting to look at how it flows and how it accounts for the growth of volume here. And I'll just draw one picture of that and then stop to show you where the volume is flowing here. So here I'm drawing the case of a black hole that forms from collapse. It has some final slice in here, let's say, that looks like that. And I'll just draw two different time slices. Make sure I get this roughly right. Okay. So if I want to know since it's a conserved current, the difference in the volume of this slice and this slice is just going to be accounted for by the flux of this gate current across the horizon. That flow vector field looks something like this over here. So there's some change of volume there, delta V, which is equal to the flux of this unit time-like vector across the horizon there. And if we didn't make the horizon the cutoff surface, but suppose we had picked, as is usually done, some surface out here at very large radius where nothing is happening, then what we would have found is that all the flux of current across here, so there's no change because this is just a stationary space-time out here between, what am I saying here? There's no change in the flux through here, but this flux is accounted for by flux in from at greater radius to the left. So basically what I'm saying is that complexity flows from the ultraviolet in the field theory to the infrared. And that interestingly matched a picture of how CFT states thermalize in the perhaps opposite way from what you would expect. They thermalization proceeds from UV to IR in a strongly coupled CFT. I say that only because there's an interesting paper by Vijay Balasubramanian plus 9 co-authors from 2011 where they studied holographic thermalization and found that, in fact, it proceeds from UV to IR. And so the same thing seems to be true for this complexity. But I think the real physical interpretation we should have of this is the following. Wherever you put this cutoff, it's like saying anything at shorter scales, that's just a vacuum. I don't have to pay the price of constructing it. That's my reference state. But I'm only going to count the complexity associated with building up everything besides the vacuum, starting at that length scale and going longer. And really, but nothing is happening until you get down to the thermal scale. So if you move that cutoff scale, it's just not going to change the rate of change of the complexity, although, of course, it'll change the absolute value because you're asking yourself to construct the vacuum between this cutoff scale and this cutoff scale from some random reference state. Okay, and finally, I think I could just say that I could get this formula for the complexity by looking at what is this volume? Roughly speaking, it should go like, so this section of the final slice or of this surface, this section of this surface, basically it's like a cylinder. Its cross-section is a sphere, and it has some length. The spherical cross-section is basically got an area equal to the horizon area. It's the same order, no matter which black hole we take, and no matter as we go late in time. So I would say that this delta V goes like the area of the final slice, which is the same as the area of the horizon, so I'll put area of the horizon, times this length, delta L. Now what is that length? Well, the metric tells us what that length is. So this is basically, on the final slice, it's an orbit of the killing vector. So it's the norm of the killing vector times this amount of killing time. So the length here should be the norm of the killing vector. I'll call that alpha, the lapse function, at the final slice, times delta t, the change of the killing time. But now the norm of the killing vector, well, that depends on how far you are away from the horizon. The norm is 0 here, and then it has some gradient. And by Taylor expansion, we can estimate the norm as the surface gravity. This is how the surface gravity is defined. It's the rate of change of the norm of the killing vector times the proper time from the horizon to the final slice, or to whatever slice I'm on. But I just said before, that time is tau f. So this should go like kappa tau f. And if you look at this and say, oh, but the area is basically the entropy of the black hole. So basically this delta V becomes the entropy of the black hole times delta L, but delta L is kappa tau f delta T. Kappa is the temperature of the black hole, times tau f times delta T. So if I want to find the rate of change if I want to find ST, which Lenny argued should be the rate of change of complexity, I should divide the volume change by this tau f. So this is a picture of why it is that this time is the relevant time to divide the volume by, given the assumption that what you're trying to come up with is S times T. So we don't have a independent derivation except to match to the ST expectation. But we're not just matching formulas, it's at least got a rationale generically. I better just stop there.
Alex, do you want to take the microphone?
Oh, thank you.
Yeah, sure.
Thanks. Good, thanks. So this should reassure you, even people that work here don't know how to make this work. There we go. Okay, so what I just want to do, I guess I have 5 minutes, so I'm going to keep this super short. But I should say that just like just like Ted, I haven't been working on complexity for very long. We kind of stumbled upon it by accident in some work that I did with Aitar Lefkovich and Gabor Sorozi. But one thing that sort of bothered me from the get-go on complexity is that if you cannot tell me what complexity is in the field theory, then what are we doing in the first place? So that's why I very much like this recent work that Rob talked about trying to define complexity in quantum field theory. And so here's a very gross sketch of a field theory space. And I'm going to call this axis N. And this axis will be the coupling axis, like the TOF coupling. And so I think what we kind of understand right now is this corner here. Free field theory, one free boson or one free fermion. Maybe you can turn on perturbative couplings a little bit and talk about a few fields. But of course, what we would really like is one definition that works for everything. And I don't know how to do that, but what I want to do in the next 2 minutes is give you a definition that works in the opposite corner. This is where you have a large N theory that's strongly coupled. And so to do that, I need to introduce a set of a space of states in these types of theories, which are the following. They're states that you create by doing the Euclidean path integral with some sources turned on. And there could be sources for multiple operators, and the operators that I'm going to allow you to turn on are the single trace operators. Okay, and then the wave function for such states, I'm going to call, sorry, this is not the TOF coupling. These are different sources. Let me call this G or something. Then the wave function is just given by doing the path integral with boundary conditions with these sources turned on. So I don't have time to get into this, but we've been gathering evidence that these states are the CFT states dual to semi-classical geometries. Now, once you have these states, what you can do is define a metric on this space of states, which is just given basically by the pullback of the Fubini study metric onto this space of states. Okay, so the Fubini study metric is the natural metric on the Hilbert space, and you just pull it back to these lambda states, and you get some metric. And the formula for that metric, if you want, GAB, is just the following. You take, I didn't say it, but obviously the brass states are just given by the same path integral, but where you conjugate the sources. And so then you do the following. You do this sort of symmetric variation. Oops. So this acts on just the log of the partition function. And so this is the expression for the pullback of the Fubini study metric onto the space of states. Now, once you have a metric on the space of states, you can ask, what are distances on the space of states, and you can try to write down a definition for complexity, which is a path through the space of states. And you need to introduce some cost functional that you're going to extremize over. And we don't really know right now what the right cost functional is here. There's several natural ones that you could write down. The first one is just saying, it should be just the geodesic distance. This is a nice one. It's parametrization invariant. There's some problems with this because if you have two uncoupled CFTs, you expect the complexity to be additive. It shouldn't matter how you couple the two CFTs are uncoupled, so the complexity should just add, and this will not happen here. So we thought it was slightly more natural to do the kinetic energy, which is just the following expression. And so this has the problem that it's not reparametrization invariant, so in some sense you'll have to specify how you're running the circuit here. But you can just take this definition and run with it and see what you get. And so we worked out a few examples like Bagnado's geometries close to the vacuum or some sort of mini superspace thermal field double. and we could get nice qualitative agreement with what you expect from the bulk. But okay, so there's still a lot to explore, but what I just wanted to write down is some type of field theory definition of what complexity could be. There, I hope I did 5 minutes, not more.
So now it's up to you guys. What do we do?
We should, I guess, answer any questions
We can
on
take
this
10
sub-
minutes for discussion, but please use the microphone.
So since Alex just spoke, I'm just wondering what in the one of the sets of geometries you could consider making this way is black hole states. So
Yeah.
which definition of the length in this, what function of the Fubini study length or whatever is the right, gives you what Lenny's expectation for the rate of change of complexity?
Oh, okay. So, yeah. Well, it depends if do you have in mind a black hole formed by collapse, or are you happy with a two-sided black hole?
I guess at this point, either one.
Either one. Okay, so the two-sided black hole you also get in similar ways by doing the path integral over, this time not a hemisphere but a cylinder with sources turned on. And you can play the same game and do all of this. And for us, the natural scale, I mean, sort of the only scale that you have in some sense to put for how the time is running is the temperature. So I don't know how that would, this was for planar black holes. So in some sense, there's no small and big black holes. So
could you check it on small and big ones?
we could in principle. We haven't.
And do you
We
know
should.
that it's not just the length in the Fubini study metric in that case also? I mean, would that be equivalent in that case, or do you have to take this?
You have to
choose a
specify
parameter.
this it's some sort of additional state dependence.
So you can show that the length function doesn't work. That's really what I'm asking?
Yes, yeah. Oh, well, even here, even in the planar black hole, you can show that this does not work.
Okay.
Yeah. You get a growth that is faster than what you expect from the bulk, and so this cannot possibly be the right.
This meaning the square root?
The square root cannot possibly be the right thing. Yeah.
Thank you.
What part of your definition depends on having strong coupling?
Okay, so large N is obvious because I talked about single trace operators. I think it would be interesting to try to move a little bit here. Our whole picture relies on the fact that basically there's a nice phase space of the gravitational solutions, and you can map that phase space to the sources that you turn on. And once you start adding this, you need to start worrying about many more fields in some sense. And so in principle, I don't think there's a sort of an obstruction in principle to trying to do this, but it's much more complicated. And so there's many more fields that you need to take care of, and so you could even worry a little bit about just doing higher derivative corrections if you wanted to explore this a little bit. But also, we don't know what's supposed to happen in the bulk, right?
So your definition uses the bulk?
No, our definition is a CFT definition, but the reason we believe it is because, in some sense, we know that there's an Einstein gravity dual. We know that the phase space is under control. You just specify the metric on some slice and maybe some scalar fields, and you're good to go. Certainly in this corner here, where you would have a higher spin theory, for example, then it seems much worse because you have an infinite tower of massless fields, and you need to get them all under control. But, okay, one could try to work perturbatively around here.
Could I interpret your choice to restrict to single trace insertions as a choice of basis for what you're calling simple gate operations?
Well, the first thing that I didn't have time to say, I guess, is that these are not unitaries. We're building states with the Euclidean path integral, so this is not, there's no, I mean, they're Euclidean unitaries or whatever you want to call them, but they're not unitaries in the sense that Rob talked about. So it's a little bit, the construction is a little bit different. It's more closely related in some sense to the other picture that Rob talked about where you're trying to optimize Euclidean path integrals by Tadashi and other people. It's also different from that because in some sense in that story you're trying to optimize a norm. In some sense the path integral is some overall norm of the state that you're trying to optimize, and I'm not exactly sure what that means. Here, because we use the Fubini study metric, we're norm independent. But it lies somewhere in between, if you want, the path integral optimization story and the unitary story.
I see. So I guess I was just wondering, is there a place for doing deformations like sources that are, say, like double trace or multi-trace? Like,
wait a few months or a few
okay.
weeks, I don't know. So I didn't say this, but these, you should think about these as coherent states in the quantum gravity path integral, and double trace operators would correspond to squeeze states. Those probably also make sense, and then triple trace and higher moves you out of that sort of classical phase space, I think. Yeah.
If there aren't more questions, I have one. So this is for all the complexity folks. And it elaborates on the question I was just asking Rob. So let's think about a black hole that we make and it evaporates. And there's a similar set of slices there, which have this linear growth with time, basically. But once we've gotten past a time of order r cubed, which is the half-life or the evaporation time of the black hole, I think one of the messages of unitarity and the need for unitarity is that we shouldn't really trust the description of the geometry in terms of those slices any longer at that point. So, I think in this general story, that's when things are getting interesting in terms of, trying to make these identifications with complexity. And you're saying, I have this geometrical quantity, which I am supposed to be identifying with this field theory quantity, say, on the boundary. But really, on the geometrical side, it's not clear that I should trust that as being some sensible thing, because of what I just said. On the geometrical side, yeah.
You mean the entire space-time geometry?
Yeah, well, or at least the geometry inside the black hole. I'm trying to learn things about quantum black holes, but by the time I get this by the time I get the interesting growth in the geometry in the classical black hole or semi-classical black hole, I can't really trust that picture any longer. So that's kind of a puzzle about, more deeply what the thinking and motivation is. And I'd just like to put that out there to see what you think.
But so what if I say the following words? I don't know how to say it for the collapse story and the evaporation, but if I take the eternal black hole, I could compute a two-point function on one side, and I know that there's a time at which I can't trust the geometry anymore. Right? And that time is like exponential in the entropy.
Yeah, I think, again, a black hole in thermal equilibrium is in some respects, just like a collapsing black hole, but it's in a bath. And so, you might ask, why could I get away with trusting the internal description, to such incredibly long time scales when I can't trust it if the black hole is just, freely evaporating. Yeah, so I don't know. It seems like it's worth thinking more deeply about that, but I don't know if there are further thoughts here.
No, the only thing that comes to mind is you might think about, what are the values of the complexity, in this regime where you think that the internal space-time is breaking down, and I suspect that it's far, far less than Lenny's E to the S.
Yeah, it's a short.
And so something. Yeah. But it's saying there's something then interesting happening. Well, if we can follow through and we really think this is complexity, it's saying something really interesting is happening at that at that time scale in this circuit picture. But that's just I don't know what else to say.
Well, there were 3 words on the blackboard. Were they left for this discussion or for?
Sure. I don't know.
We have a couple of minutes.
I can't read from over here.
You can put them on the lower board. Then.
Yeah, we can hide them.
Well, the singularity, yeah.
It's actually in tune with what Steve was saying. This is just an extreme version of what he said, because in this case you could say, okay, maybe this doesn't happen.
Well, I was going to say something else, which was that if you go into the guts of the complexity equals action calculation, having a contribution from the singularity or the region very close to the singularity is essential to getting that answer, dc dt equals 2m. And so that's annoying because, what's really happening at the singularity. And all I'm saying is that it's annoying. In some sense, complexity equals action probes too close to the singularity because you go right up to the singularity. In contrast, as Ted was saying, complexity equals volume doesn't probe close enough because it gets hung up. Okay, it's not a problem, it's a feature. But well, you might ask, if interesting, if there's an interesting episode of Star Wars happening here, will we ever see that in the complexity? So it's, okay, it's sitting there, it's not on the screen. There's lots to explore. That was my message. There are other issues that you can talk about for the singularity. If you think about higher curvature theories, we don't really understand, like people have studied, say, Gauss-Bonnet, just because it's something you can study, and there are issues with taking the limit where you turn off the higher curvature coupling. You don't get back to the answer that you got in Einstein gravity, but it's because of the sensitivity to the singularity. So there are issues there. I don't have any terribly insightful answers. I keep going? Or
maybe I can make one more comment related to that. So I actually think that the timescale, the relevant timescale is not E to the S. In this case, it's actually, depending on how you define it, it's either S or square root of S. Mm-hmm. And so if you could find that timescale in your calculation, it would be instructive.
Yeah, I'm not sure that you would find that timescale as a unique timescale, but it would certainly say something. What I was doing was turning it around. It's saying that our intuition about, or Lenny's intuition about the growth off to, this saturation at exponential times, that there's somehow shortcuts or something interesting is happening at a much earlier timescale, which I think is interesting because, I won't.
This is what I
mean. Yeah.
Could you say something about the scale issue? Like basically just amplifying the comments at the very end of your presentation.
Yeah, so I didn't really get to talk about that, but in defining the action, there are issues related to, I'm just repeating things for the rest of the audience, that I have to introduce boundary terms. In particular, I have to introduce boundary terms on the null surfaces of the Wheeler-DeWitt patch. Those depend on having a normal vector. The norm of the normal vector isn't fixed. And so you ultimately, because of that, you run into ambiguities in defining the value of the action. If you take the variation, there's no ambiguity in the variation of the action, but assigning a value to the action is ambiguous. Ultimately, there's a thing that we call the boundary counter term, or it's something that ensures the reparametrization invariance of the null boundaries. In our paper, it got shuffled off to an appendix because we'd been lurking on the paper so long we were tired and just wanted to get rid of it. But it turned out, and it was really Simon Ross, I think, who was the first one to point out that maybe it's important to include that particular term. And we showed later on in the Vadya metric, which you talked about, that if I want to reproduce the switchback effect properly, I really need to include that term. Otherwise, you get, nonsense answer, or you get answers that would not be consistent with the switchback effect. And so it seems when you define the Wheeler-DeWitt action, you better include that particular contribution. There's still a scale involved there, in that it involves an integral of something like theta. So this is the expansion. but that's a dimensionful thing. It's theta log theta, and so there's a scale that you introduce there. So the ambiguities about the norm of the null vector disappear, but there's still an ambiguity here that comes into the game.
And were you saying that all these ambiguities match ambiguities in your microscopic calculation?
I was probably saying something like that, but it was an aspiration, not a statement of fact. I mean, there are other calculations that we're doing now which seem to, that picture seems to be falling apart a little bit, so it's not clear anymore. But at the time, well, it was a real surprise to me that, you know, we had done this calculation in holography, and I found something that was kind of disturbing, or at the time it was disturbing to me, kind of made me start to doubt. And then when we did the simplest field theory calculation, very similar ambiguities popped up. And so it seemed that it was just one of these things that, you know, complexity is a new kind of a beast, and we just have to understand what its properties are and come to grips with them. In the same way that, you know, I think there was a similar story when entanglement entropy came into the game in holography. There were new kinds of properties. There, you know, the UV divergences that you mentioned for complexity that were perplexing to you. Well, you know, I actively ignored entanglement entropy for 4 years because of those same divergences, and I thought this is all nonsense. And so the lesson I learned is, don't worry, just keep going. And I can add there that, well, I'm sympathetic to your perspective. You know, what you learned in entanglement entropy was, well, there are problems with the entanglement entropy itself. Sometimes there are universal terms that you can identify in a unique way. But another thing you can do is you can think about differences of entanglement entropies. You know, so sometime when somebody was talking about the mutual information, you know, the way we understand that is as a difference of entanglement entropies, and one of the key features is that you eliminate those UV divergences. So in the same way, you know, this complexity of formation that I talked about, you could compare, I mean, what you were saying, where there were all these problems, or there were these issues out here, there's a lot of stuff that you're not interested in. That's basically the same as in the vacuum. So if you subtract off the vacuum contribution, I'm going to get a finite answer, and I can think about well, that difference as being an interesting quantity that tells you about the robust or the interesting finite stuff in the evolution of the black hole. I mean, I focused on a calculation on a t=0 slice, but in our thermofield double paper, you know, we did the same subtraction up here just because it's an easy way to get a finite answer that you can put on a plot.
We should stop for a little break. Okay. Thanks to the three speakers. And let's come back at 10:40.